I've been suffering from disk space anxiety, so today we're going on a bit of a side quest and upgrading my NAS to support over 1 petabyte of raw storage. You've probably seen petabyte NAS builds from other YouTubers, but this video is going to be nothing like those. We are going to be literally designing and building this box from scratch. That means over 100 3D printed parts, over 20 meters of wiring and over 100 crimps, and over 30 custom circuit boards. By the end, we'll have this box which stores up to 45 hard drives. That means if you use 24 terabyte drives, it's over 1 petabyte of storage. Also, since we'll be using Noctua fans and consumer power supplies, it's basically silent, so I can actually run one of these in my apartment without ear protection. And as far as I can tell, this is the smallest enclosure capable of holding 45 hard drives, which is good for me since I have a lot of unused vertical space but not a lot of floor space. If you're crazy enough to want to build one of these yourself, all the parts are open source with links in the video's description. So you might be wondering how the heck we got here. If you're like me, then you probably have a main computer or laptop like this. If you take it apart, you'll find that most modern computers have a flash-based SSD inside that looks something like this. At some point, you'll realize that if this fails or if you run out of space, then you're out of luck. So then you might go to the store and buy an external USB hard drive that you can plug into your computer. And eventually you'll outgrow this as well and find yourself in NAS YouTube land where people will be telling you to buy NAS boxes like these. Fundamentally, all of these NASs are just boxes with a computer inside attached to multiple disks. Then you can connect this whole thing to your home network, then any other computer on your network can access the storage. Currently, my main NAS is one of these server rack mounted HL15 boxes. Inside, there are 15 disks in the front, and a computer in the back which also has a 10 gigabit per second networking card to quickly connect this to other computers. As a quick disclaimer, please be aware that none of this actually counts as sufficient redundancy, since if your house catches on fire, you'll still lose all your data. So make sure you always have a separate copy of your critical data in one of many cloud storage services like Backplane or Google Cloud Storage. Alternatively, if you have friends or relatives, you can copy some data to their NAS in another location for redundancy. Anyway, for today's project, here's the plan. Starting out, I already have my main NAS, which has a bunch of existing components in it like a CPU, motherboard, a power supply, disks, and fans for cooling. In this video, we're going to be making a second big box which will hold a lot more new disks. The disks I'm going to be using are these Western Digital HC550 hard drives. Compared to the SSDs in my main computers, these are much slower and much bigger. The performance difference won't matter too much since theoretically if we have a bunch of these disks, we can match the SSD performance with parallel reading and writing to the disks. As you can probably guess, there are lots of other bottlenecks that won't let us go quite this fast, but we definitely have plenty of headroom to optimize. Where classical hard drives still reign superior though is cost. If you're just comparing the disk costs per terabyte of storage, hard drives are still an order of magnitude cheaper. Note that this is pricing for refurbished or used drives and does fluctuate a bit over time. I should also mention that both SSDs and hard drives come in consumer and enterprise variants. The consumer SSDs aren't very good for NASs since they are much more likely to lose data if you lose power to your house and don't have a battery backup. The enterprise SSDs do have extra capacitors to handle this, but are harder to come by. You can use consumer or NAS branded hard drives for small NASs since they don't have the same fundamental issue, but if you want to run more than 8 of these side by side, you need to use enterprise drives like the ones we will be using since they have better heat and vibration resistance. Anyway, besides the drives, the new box will also have a power supply to power the drives, and some fans to keep the drives cool. We're also going to need to have a mini motherboard to handle turning on and off the power and controlling the speed of the fans. So far this is mostly the same as the main NAS, but instead of putting a full Intel or AMD CPU in this box, we're going to just run some wires from the disks directly back to the main NAS's CPU via some adapter boards. Usually you'll hear this setup being called a JBOD or just a bunch of disks. This way, by not having a full second CPU and motherboard, we can cut the space and cost requirements a bit. If you are very adventurous, there is enough space in the back of the box to hold a Raspberry Pi or something like a COM7 module, so you could mod this to be a full NAS if you really wanted to. Anyway, now we'll actually start the build. The foundation is going to be this steel frame. Usually on this channel I like 3D printing things to make it easier to make, but these drives are fairly heavy and I don't have a lot of confidence in plastic holding up 30 kilograms once this thing is rack mounted, so the core frame pieces of this build are going to be made of steel. Note that if you want to make one of these that's always on the ground, that you can probably replace this with high temperature plastic parts. The cheapest way to make one of these is to use a sheet metal cutting service like SendCutSend. By the way, this is not a sponsored video. Their tolerances aren't particularly good, but they are cheap and fast, so I ended up using them and all the parts are designed to work with generous tolerances. Anyway, in your CAD software, you'll need to start with designing a shape that can be unfolded as a 2D sheet of metal like this. This shape will then get cut out with a laser from a big sheet of steel. Then the sides will be bent to reach the desired shape. Here's a quick clip from the SendCutSend YouTube channel in case you're curious what the bending machine looks like. The exact material I ended up going with is this G90 steel. This is basically steel that was pre-plated with zinc before it is cut to prevent rusting. This is not the standard material used in computer cases, but is cheap and quick to machine since it doesn't require any post-processing steps. The main issue though is that when it is cut by a laser, there will be some metal exposed in the middle that isn't zinc plated, so will rust over time. This will take several months to show up and shouldn't be much of an issue overall, if you don't care about the appearance. You can also use other steels, but you need to get them either electroplated or powder coated after being cut to prevent rusting over time. The other neat feature offered by most online services is that you can get hardware like press-fit nuts inserted into the sheet metal. This will make installing this thing easier since you don't need to hold a nut from the other side when installing screws. I also got some of these threaded stubs inserted into the bottom side of the frame, which we can use with nuts for mounting things. The neat thing about these is that they are press fit such that they are basically flush with the other side of the metal, so don't take up more vertical space than needed. You can also get standoffs pre-inserted, but they didn't have any in the size I needed, so I ended up manually installing some with low profile screws from the bottom side. Each of these white pieces is 3D printed plastic that has these copper threaded inserts heat pressed into both sides. Next, we're going to be installing power supplies to power the discs. I ended up going with this SFX form factor power supply I got for pretty cheap off eBay. If you've seen PC power supplies before, you might have noticed that they have this label on the side that shows how much power you can pull at different voltage levels. Hard drives only really care about 5 volts and 12 volt power, so these numbers are the only ones that actually matter. If you look at the datasheet for one of the hard drives we are using, they peak at needing 1 amp of 5 volt power and 2 amps of 12 volt power. Note that we will be using staggered spin up, so it's unlikely that we will hit this across all the drives at the same time, but I'd like the provision to be able to handle at least 80% of the peak combined usage. If you do the math, this is way above what our power supply can handle. You can get power supplies with higher 12 volt ratings, but there aren't really any consumer power supplies with high enough 5 volt ratings for this project. So instead I ended up getting 2 power supplies. And basically we will be dividing the disks into 2 groups, where each one will get power from one of the power supplies. Note that most proper servers also have 2 power supplies, but they are redundant, so if one fails, the other one can take over the entire load. Unfortunately though, most server power supplies are really loud and really long, so I ended up not using them. If I were to do this project again, I would probably add 12 volt to 5 volt converters to all the backplanes we make in the next section to allow using a single power supply, but for simplicity I opted for just using 2 non-redundant power supplies for now. Anyway, the power supplies will screw into the steel back panel I made. Then we can just slide the back panel onto the main body frame. This panel will be held onto the main frame with a nut going through one of the bottom stubs and screws through the side of the frame. Next, we're going to make 12 of these backplane boards. On the top side of the board is a power connector that will get power from our power supplies. Then in the middle, we have these top connectors for connecting our disks. If you're curious, this is the schematic view for one of these connectors. There's basically a ton of power pins, a single pair of pins for receiving data, and a pair of pins for transmitting data. The only tricky thing about designing this board is that the receive and transmit wire pairs need to be laid out so they're basically in parallel to minimize noise, since up to 12 billion bits will be traveling through each pair of wires every second. If you actually try to design one of these boards, also make sure you check with your PCB manufacturer for what trace width and spacing you need to get a 100 ohm impedance line. Another feature you'll see in these high-speed boards are these curvy lines. These are added to make the total length of both the 2 wires the same length. This is mainly relevant at higher speeds, since the longer of the 2 wires will take longer to send each bit to the other side, and you ideally want each of these 2 wires in the pair to finish transmitting their bits at the same time. Then, all the data wires go to this connector on the bottom side of the board. If you haven't seen this connector before, it will attach to these mini SAS HD cables. These are basically 4 regular SATA cables in one, where usually one SATA cable is enough to connect a single disk in a regular computer. So to make these boards, I ordered a bunch of these bare PCBs. Then you've got to layer on solder paste onto each of these with a stencil, and then you can place on all the components. These all go into an oven which melts and hardens the solder to join everything together. You've probably also noticed that I'm using this 3D printed holder to hold all the boards in the oven. The main reason for this is that all the connectors stick out slightly below the bottom of the board, so I can't lay the boards onto my flat oven sheet without lifting them. If you want to make one of these 3D printed holders, you can probably use any plastic since the load on the plastic isn't very high. Personally, I used a annealed Pusherman PCCF since I need this thing to survive several cycles of use. Anyway, after coming out of the oven, we still need to hand solder all the remaining through-hole components. The easiest to install connector actually ends up being these SAS connectors, which are literally just press fit without any soldering and use some mounting screws. Once you're done with all that, you'll end up with a big pile of boards that looks like this. Now what's the chance that I made over 1,000 solder connections perfectly on the first try? Best case, if there's a bad connection, some of the disks just don't connect. Worst case, I break over $10,000 of disks. I'm not taking any chances, so we're going to test every single board before installing it. The classical way to do this is to grab a multimeter like this to measure each board. If both probes of the multimeter connect, then we know there is a connection between the 2 points we are probing. The only dangerous pins on this board are the power pins, so we mainly need to verify a few things with them. First, we should verify that the 12 volt and 5 volt input pins aren't shorted together. Second, that the 12 volt and 5 volt pins aren't shorted to the ground pins. And third, we need to verify that all these pins are connected all the way through to the correct pins on each disc connector with fairly low resistance. If the resistance shown on the multimeter is too high, then we likely didn't fully cover the pins when we were soldering them. Unfortunately, this process is extremely human error prone, and I'm way too lazy to do this for all the connectors. So instead, I created another custom board that has the sole purpose of testing these backplane boards. Basically how it works is you start a little command line program, then it'll first run some self-tests on the test board itself, and then it'll tell you to plug in the power connector to the backplane. It will then run some backplane level tests, and then you plug in each individual disc connector and the program will automatically test the continuity and resistances between all the pairs of pins. Finally, once all boards are tested, we can screw the boards into the frame. For now, I'm just using 2 screws since we will remove these later. All the boards are labeled with a position indicator based on this map I made in a spreadsheet. Since we are going to have a ton of wires later, this will make it more obvious which one goes to which board. The L prefixed ones are the ones that will go to the left power supply, and all the R prefixed ones will go to the right power supply. Next, we're going to assemble all the control electronics for the JBOD. The most important component is going to be these SAS expander boards that I got off eBay. We're going to have 2 of these, where each of these will take as input 1 cable from the main NAS and expand it out to 6 cables going to the 6 backplanes from one of the power supplies. The numbers in this screenshot correspond to the numbers in the backplane IDs. Unfortunately though, these cards are way too big to fit in our case, so we're going to remove the end connectors that we aren't going to use. Just like the SAS connectors on the backplane, these are just screwed on and can be pulled off without any desoldering. Once you've done this twice, you'll end up with 2 cards that look like this. To allow the entire JBOD to be connected and disconnected easily, we will also have this adapter board I got off Amazon and converts between a beefier external SAS cable going from our NAS to the 2 SAS expanders inside the box. Lastly, I custom made a mini motherboard for the JBOD. Once it's fully assembled, it ends up looking like this. The functionality of this is similar to a real computer motherboard. Normally, if you have a PC power supply and try measuring the output voltages, you notice that there is basically no power coming out. Only if you bridge 2 special pins on the power supply does it actually turn on and start supplying power. If you have a desktop computer, this is what the motherboard does when you press the power button. On our mini motherboard, we have these 2 connectors here coming from the power supply with the pins we need to turn on the power supplies. Then instead of having a physical power button, microcontroller will receive a command over USB from the main NAS telling it to turn on when we want to access the disks. When the power supply is turned on, this board will also distribute power to the SAS expander boards and to all the fans and LEDs we have, similar to a regular motherboard. Anyway, here's all the electronics we will put together along with a few additional screws and wires. Everything will be mounted on this 3D printed carrier board, which has magnets on the bottom for sticking to the steel frame. We'll start by attaching some screw brackets to the SAS wire adapter that we will be using to mount it to the back of the steel frame later. I am also hot gluing the nuts in place since they won't be accessible to tighten later if they come loose. Then the cable adapter board goes onto the 3D printed carrier board, and then we can screw on the main motherboard. Note that the standard 4-pin PC fan connectors have a notch on one side to prevent them from being inserted backwards. The 3D printed carrier board has a corresponding cutout that only allows you to insert these connectors the correct way. Anyway, next we'll attach the cables that will power the SAS expanders. Also, I soldered together a USB extension cable that will route the USB port out of the back of the frame. This goes into a 3D printed holder that will get hot glued in place. Once the glue dries, we can plug in the cable. Lastly, the SAS expanders will be stacked on top of the main board and we can plug in power to them. Note that the SAS expanders also have a PCIe connector, which is just used for providing 12-volt power and is redundant with the 4-pin connector that we are using. Also, you only need to connect 2 of the 4 pins, since typically the other 2 pins are used for providing 5-volt power, which the expanders don't use directly. And here's the final stack up. This whole stack just slides into the space between the 2 power supplies, and we can screw in the connectors on the back side. Next, I'm going to be making all the power wires that go from the power supplies to the backplanes. This starts with me measuring roughly the wire distance from one of the power wires on each backplane to the power supply. Then for each wire bundle, we'll cut more wires of the same length. There will be 2 black wires for the ground connections, 1 white wire will carry 12 volts, and 1 blue wire will carry 5 volts. Note that every backplane needs dedicated wires back to the power supplies, since individual wires and pins can't carry enough power without significant losses for many disks. Then I'll be crimping one side of each wire bundle to attach it to these 4-pin connectors for the backplanes. To keep things organized, I have this heat shrink label paper. Basically, I can print text labels on these using my label maker. Then they fit over the wire bundle and shrink with some hot air. Then we just need to do all these steps 11 more times for the other wire bundles. As you will discover in a few minutes, the wiring situation is going to be a crazy mess and impossible to debug if everything isn't properly labeled. Once I have one side fully crimped, I'll try inserting them and trimming the cables if they are still too long. The other side of all the wires then needs to be crimped to connect to these connectors on the power supply. Beforehand, I reverse engineer the pin out of my power supplies and it looks like this. The red text is the IDs of the backplanes that each pin will go back to. There's also an MID for the wires that need to go back to the motherboard. Also, if you are doing this yourself, don't accidentally use the blue pins, which are sense lines and can't be used as dedicated power lines. If you try measuring the voltage, they will appear as ground 5V or 12V, but you can't actually pull full power through them. As I found out the hard way, if you find a pinout diagram on the internet that doesn't have these pins on it, then it's probably lying to you. Anyway, once you are done with all the crimping, you end up with two big bundles of wires that look like this. We can then plug these into our power supplies. Now you might be asking, what's the chance that I correctly wired up all 100 pins in these wire bundles correctly without any mistakes? If we turn on the power supplies, we can use the multimeter again and manually verify that the voltages are correct. In particular, we expect to get 12V across 2 pins and 5V across the other 2 pins. Of course, this is also prone to human error since I might measure the pins backwards and get a negative reading. So I ended up making another dedicated testing board. The wire on the right will go to each of the connectors in the wire bundles. The red wires on the left go to a multimeter I have which measures the voltage across the 2 red wires. The board itself has some relay switches to change which pair of wires the multimeter is measuring. So basically you plug in one of the wires, then you can run a program on your computer which tells the multimeter to first grab the 5V measurement, then it'll switch to the 12V line and measure that. Then you just need to repeat this for all the wires. Before we go forward, I'm going to assemble these steel plates that are going to hold the fans since it's easier to route the fan wires now before we make a huge mess with everything else. These plates are fairly straightforward since it's basically just Noctua fans attached to some plastic TPU fan spacers. The front plate just goes on the front of the case and we can plug in the fans into the motherboard. Then the front panel just screws on using the captive nuts in the main frame. This is also a good time to plug in the SAS cables going from the rear connector to each of the expanders. If you're wondering why the second cable is so long, it's because I can only get these cables in fixed length increments without ordering custom ones. Now we can mount the mid-fan panel which mounts to the main body in a similar way to the rear panel with screws and nuts. Finally, here's what the wiring in the back looks like so far. Now we can finally finish wiring everything up. Note that if you buy these SAS cables, they will look like this. The wire in this build ended up being very tight, so I ended up removing these sleeves to make these wires more packable. If you really wanted to make these smaller, you can also cut off these multicolored wires, which are for sideband signals which aren't used in this build. Anyway, back to the wiring. We are doing this from front to back to make it easier to plug everything in. Other than that, this is basically just the game of matching up the numbers on the backplanes to the SAS expanders. In the end, all the wiring looks like this. At this point, the main remaining risk for something breaking are these solder joints on top of the backplanes. If I didn't solder them low enough, then when we plug in a disk, some of them may end up shorting together and something might catch on fire. To de-risk this a bit, I laser cut these plastic separator pieces. This ends up looking like this and just installs over every backplane. Lastly, I also 3D printed these floor panels. The main purpose of these is to prevent air from going under the backplanes, since we ideally want to force all the air between the disks to cool them. Next, we are going to assemble these disc retainer pieces that will prevent the discs from moving side to side. This is made of 2 3D printed halves since my 3D printer can't print the whole thing in one shot. These are a bit over-engineered at this point as the spaces between the discs are slightly hollow to grip onto the discs when squeezed. The first step to assembling these is actually to first create these LED strip boards that will end up going on top of the 3D printed pieces. The LED strips look like this, and we're going to have 60 LEDs in total. The LED strips screw into holes on top of the 3D printed pieces. Note that the orientation doesn't matter for now, since I'm just screwing them on to verify the alignment of everything. Then I have these steel pins that will be super glued into both sides of the 3D printed pieces. To actually make sure the gap between the 3D printed pieces is correct, I'm now screwing on the middle LED strips, which bridge the gap between the two sides and will only fit if the gap is the right size. Lastly, we can flip the whole thing over and wait for it to dry with some weight attached to try to make everything relatively flat. Once the glue is dried, we're going to follow a similar pin-based process to attach these side flaps. These are not structurally critical and are mainly to further guide the airflow in the case. Once the glue all dried, I remove the LED strips and attach the whole piece to the main body with some screws on each side. We are now going to reinstall the LED screws in the right orientation on top of the disc retainer. These will basically be wired up to light up in one long line that lights up in a zigzag pattern as shown here. Upon hearing this, you might be wondering how the heck we're going to wire up these pins to these pins. Well, I ended up making yet another custom board, which is a wire bridging board. This is made of very thin 0.8mm PCB material. The standard PCB thickness is usually 1.6mm. This will mount between the LED strips like this. Then we just need to solder everything in place. Once everything is soldered, it looks like this. Somehow this ended up being the only place in this build that required a botch wire since I messed up some of the pins on the strips while soldering them. Just to test everything, I made a test program that cycles a green color through the entire strip. Finally, we are almost ready to actually put all the disks in. I'm going to be connecting everything to this test computer, which is going to stand in for my main NAS computer until I know everything works. I'm going to be connecting this SAS HBA card to the computer, which will allow us to access our SAS devices from it. Then we can use some cables to wire up the JBOD to the computer, and we also need to hook up the USB connection for controlling everything. The final wiring looks like this. From the computer, I have this UI from doing manual test operations and monitoring the state of all the disks. First, I had to turn on the power and make sure the SAS expanders register as connected. Then I'm going to start plugging in disks. It does take a few seconds for the operating system to realize that a new disk has connected, but then it'll eventually show up in the UI, and I also configured it to make the LED around the disk blue if it is connected and healthy so that I can visually know where any bad disks or connections are located. This is only possible because we wired up the backplanes to specific numbered ports on the SAS expanders, so we know the exact mapping of physical bays to ports on the SAS expanders. And in case you're wondering, it doesn't matter which way we attach the cable to the main host computer since we stagger turning on the power supplies, so we know which expander is which based on the order in which they show up on the host machine. Eventually, we will have all the disks installed and registered in the UI like this. The airflow inside of the case isn't ideal yet since it has no top cover yet, so I also made this cover that screws onto the top. The design of this is heavily inspired by how the cover of the 45 drive's HL15 works. It starts with another thin piece of bent sheet metal that looks like this. On the front side, we're going to glue on these 3D printed pieces that add threads for the thumb screws. Then I 3D printed these rollers, which are threaded with the drill to accept screws. These just screw into the side holes in the cover. These are going to slot into these grooves on the sides of the mainframe, so you never have metal rubbing against metal when you take on and off the cover. Then the final cover looks like this. For people like me that like rack mounting things, this case does support rails that screw into the side, and then you can slide the whole box into your rack. The rails are the same ones as the ones that are used in the HL15. So now all the hardware for this build is done, so now we just need to figure out if it's any good in terms of performance. To rehash the current setup, we have 45 disks roughly evenly connected to our two SAS expanders. According to the datasheet, the max transfer rate of each disk is supposed to be around 200 megabytes per second, which is around 2 gigabits per second. So in theory, across all of our 45 drives, we need around 80 gigabits per second of bandwidth to fully utilize all of these disks. For the connection between the SAS expanders and our main computer, we use one mini SAS HD cable per expander, which each internally has 4 full 12 gigabit per second cables. So in theory, we should be able to get a full 96 gigabits per second of transfer rate, assuming there are no undocumented throughput limits inside of the expanders. But my SAS HBA is connected to my host computer's CPU via a PCIe 3.0x8 lane, which only has 64 gigabits per second of bandwidth. So in theory, 64 gigabits per second of transfer speed is probably going to be the bottleneck. Note that this means that even though our HBA has 4 ports, can add another JBOD to it, but peak throughput won't get any better. In general, this is why higher end NASs like my HL15 will have more PCIe lanes dedicated to each drive, either by directly wiring to SATA ports on the motherboard or directly to an HBA card without extra expanders. In general, my main goal right now is to fully saturate the 10 gigabits per second bandwidth in my network card, so I'm not super concerned about the performance right now. The other important factor for performance is the file system. Across all the 45 drives, I'm going to be setting up a ZFS file system using RAID Z2. To be more specific, suppose I have some data to store like hello world. To store this, I'm going to have ZFS split this into 4 chunks that look like this. ZFS is also going to compute 2 more special parity chunks derived from the first 4 chunks. Then it's going to pick 6 separate disks and store this data on those 6 disks. Normally, if you want to read back the data, you'd just read the first 4 chunks. But if some disks randomly fail, as long as 4 of the 6 disks are remaining, you can still do some calculations with the parity chunks to recover the original lost chunks. The math behind this is known as Reed-Solomon codes, in case you want to read up on it more. Anyway, we're going to divide all 45 of my disks into groups of 6 and 7 disks that follow this pattern. Overall, what this means is that, first, we need roughly 1.5x the amount of space to store some amount of data. So even though I have 810 terabytes of disks, I can only use around 540 terabytes safely while maintaining data redundancy. This also means that writes will need to be at least 1.5x slower than having no redundancy, and probably will be slower than that because we also need CPU bandwidth to compute the parity chunks. Sequential reads will normally be roughly the same speed compared to the case of having no redundancy when there are no failing disks. The main advantage of this setup, though, is we will always be able to tolerate 2 random disk failures and possibly up to 14 disk failures overall if they are evenly distributed across the subpools. Anyway, after setting this up, I used these Linux commands to load test the file system by trying to read and write to large files. Note that we have the ZFS ARC and compression settings disabled in all these tests. And here are the results. The sequential write results are probably very low compared to the theoretical limit due to the CPU overhead of parity chunk calculation and the fact that my test bench has a really slow CPU in it. Sequential read results get much closer to saturating our transfer limits though. I could probably tune this to be much better, but for now this is good enough. Instead of tuning these more, I'm just going to wait a few days for all the experts in the comments section to tell me everything I'm doing wrong. Also, obviously the random read-write performance is much worse, but most of the software I'm going to be using with this thing is sequential read-write optimized, so I don't really care. The other big risk we need to validate is the risk of all these disks vibrating too much and causing damage over time. If you look in hard drive data sheets, they will literally have pages of specifications on how much vibration they can support without issues. Ideally, we want to stay way below these limits during normal operations. It's hard to measure all these parameters, so in a nutshell, we need to stay below 0.67 Gs of acceleration to avoid any hard errors with any of the disks. 45 Drives also has a nice blog post that describes this behavior in more detail, and they've also identified that around 0.2 Gs of acceleration is the point at which you start getting noticeable performance degradation. Obviously though, we ideally want to stay below both of these limits to avoid long-term wear and tear on the disks. To measure this, I mounted this accelerometer to the top of one of the drives with glue and reran the tests with the enclosure rack mounted. For those of you playing along at home, here's the orientation of all the axes on the accelerometer. First, I grabbed this plot of the baseline performance with all the disks spun up but no reads or writes happening aside from occasional polling of the disks to grab health metrics. RMS vibration is fairly consistently below 0.02 Gs in this setup. Now on the top left are the vibrations under sequential read operations, which boosted the RMS acceleration to about 0.03 Gs. And on the bottom left is the same, but for sequential write operations, which had about the same average increase. And on the right side are the corresponding results with random reads and writes. These seemed a bit worse due to having more short periods of high vibrations during the testing. Either way, all the numbers are well below the danger zone for operating these disks. I'd expect a professional chassis made entirely of metal to have better performance than this, so there was probably more room for optimizing the geometry of the plastic parts in this build. Also, in case anyone is wondering about the power usage, here are the numbers for that. Overall, our power supplies technically have 1200 watts of capacity combined, so there's definitely more room for optimization here. Well, that's all for this video. No disks were harmed in the creation of this video. Bye!